Alright, we ready to rock and roll?
Yeah.
Okay, here we are, rocking and rolling. So you're going to be coloring your periodic tables today, and we'll start probably in about 15-20 minutes. But let's go over all the things I expect you to know. All the things I expect you to know at this point. Okay? You should know that you have a staircase here. And the job of the staircase is to separate the left side and the right side. On the left side we have the metals. You're still talking. On the right side we have the non-metals. I'm abbreviating it, NM, for non-metals. Okay? What do we call the elements that are on the staircase?
Metalloids.
Metalloids. Okay, so those blue X's are our metalloids. Metalloids have properties of both metals and non-metals, meaning they could be shiny, but they might not conduct electricity. They might conduct electricity, but they might be brittle. Okay, those are some examples of metalloids. There is one element on the left side of the periodic table that is not a metal. That is hydrogen. Okay. Good? All right. The next thing I expect you to know is I expect you to know your solids, your liquids, and your gases. So, there are two liquids. What are they? Mercury and bromine. You guys are smarties. What do you need, huh? Yeah, sure. Okay, mercury and bromine. There are also gases. I'm going to do them in pink. Feeling in a pink mood right now. All right. What are the gases on the periodic table? Nope, that's the diatomics.
It goes from carbon all the way.
Is carbon a gas?
Yeah. Oh.
Diatomics is the L, right?
Or from number 7, is it?
That's the diatomics. What elements are gases at STP? Nitrogen, oxygen, fluorine, and chlorine. All of group 18 and hydrogen. Those are your gases. Those are your gases. Everything else that I did not circle in a beautiful color, those are solids at STP. And STP stands for standard temperature and pressure. What's the matter? Wait a minute. Stop. There. I count 11. 1, 2, 3, 4 on the top. Chlorine and argon. Krypton, xenon, radon. You could circle this UUO if you want, but it's an unnamed element. And hydrogen and helium. Those are gases. So what's the problem? What? That would be 12. Okay? If you want to circle that one. Okay. Alright, your diatomic elements. Your diatomic elements are the 7. I'll do them in orange. Nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. They start at 7, they make a 7, and hydrogen is your 7th one. Those diatomic elements when they are in elemental form, will have a subscript of 2. This subscript means there's 2 hydrogen atoms that are bonded together. They are identical, but it's still an element. I'm going to. Okay? Oxygen would also have 2. Would look like that. Okay, there you go, Rob.
Thank you.
You got it. You have a question?
No, I think we're good.
Okay. How we doing out there, my friends? Okay.
What were the ones you just highlighted there? What did you call them?
These are called the diatomic elements.
Alright, thank you.
You got it.
We have two.
They are elements, but they double themselves up. I just want to make a copy of this. Okay, the next thing I expect you to know is what these columns are called. They're called groups, and the rows are called what? What are the rows called? There's 7 of them. I'll give you a hint. Periods. Okay, there's 7 periods on the periodic table. Now, groups, up and down. What do these all have in common? They're all the alkali metals. They also have 1 valence electron, and their chemical properties are going to be similar to each other. That's a popular test question. Okay. So if they give you 4 things, if they give you 4 choices, and you find they're asking which 2 elements have similar chemical properties, you're looking for the 2 that are in the same column. Because the same column, they have similar chemical properties. Okay. Periods. What do they have in common? If you go vertically, you have the same number of valence electrons and similar chemical properties. They have horizontally, they have the same number of the rings. Yes. So the periods will have the same number of energy levels. Right? So periods, in anything in period 2, we're going to have 2 rings, that's 2 energy levels. Anything in period 3 is going to have 3 rings, that's the energy levels, and so on and so forth. Okay, any questions on that? On tomorrow's quiz, I'm going to ask you to draw a Lewis dot diagram of something. Do you remember how to do those? Okay, easy peasy, easy as pie. If you're going to draw a Lewis dot diagram of, let's say, aluminum, how many dots is it going to get? 3. 1, 2, 3, or 1, 2, 3. Either one works. Okay? The number of dots will always be this very last number. I know that's a big highlighter there, so it highlighted both numbers, but you get the idea. Just that last number. Lewis dot diagrams. That's called a Lewis dot diagram. Where's your most active metal? Ooh, I stumped you. Okay. Let's back up just a little bit. What are these called? This group 1. Alkali metals. What about group 2? Alkali earth. What about 3 through 12? Starts with a T. Transition metals. Forget about 13, 14, 15, 16. 17 are called the... Starts with an H. Halogens. And then group 18 are called the noble gases. Okay. If we look at group 1, the alkali metals, what happens to the metallic character, how metallic it is, as I go from top to bottom? Does it get more metallic or less metallic?
More metallic.
More. So my most active metal is this guy down here, francium. He's very, very reactive because he's going to lose that last electron off of his 7th ring very easily. Did we talk about my little thing here yesterday? Did I take this out? All right, let's pretend I'm the atom. My head's the nucleus. Okay? This little clip that I have here represents the first ring. It would go all the way around my head. This one would be the 2nd ring, 3rd, 4th, 5th, 6th, and 7th. So if it has 7 rings, I'm here at francium. Okay? So now pretend I'm walking around in the universe and this electron is all the way out there. Okay? Isn't it easy for you to grab that electron away from me? Because I can't reach it to protect it. My head is the nucleus. It has all the positives in it. And those positives are holding these negatives on. Well, this one is so protected by these inside rings, that's called shielding, that electron out here is very easy to remove. Right? If it was a $100 bill, I bet you'd go for it, right? Whereas if if you had an element that only has 1 ring, and I'm holding it here, and let's say there was a $100 bill right there, Jaden would be hard pressed to get that $100 bill off of there because I'd be like, boop, and I'd grab it and I'd hold really tight. So the further away from the nucleus that electron is, the easier it is to remove it because the positives that are in my head don't have as much influence over it because it's being protected by all these layers. Make sense? Okay? So, if you think about what a metal does, metals are losers. They lose their electrons. This francium is going to lose its electrons very, very easily. So he's very active. If he's out about in the universe, that francium is giving away its electron all willy-nilly. Now, back in middle school, if you had Mr. Endres, he showed you a video, or he actually showed you sodium. When you drop sodium in water, what happens? Remember that? Yeah, it explodes. Did he tell you why? Now you know. Why does sodium explode? What makes it react? It loses its electron. And it loses it pretty quickly. But as I go down this group, the electron's getting further and further away. Doesn't it lose its electron more quickly? It loses it more quickly, and therefore the reaction happens, boom, so much faster. So francium, well, I wouldn't say a nuclear explosion.
No, bigger.
It's bigger. I can show you the video on that. I was going to wait till next week, but I can show you the video on that. This francium is not only much more explosive, the thing is, it is also naturally radioactive. So this would make a dirty bomb because it would give off radioactive waste. Any element that is above atomic number 83 is going to be radioactive on the periodic table. Write that down if you don't have it already. Any element above 83. So they'll never ask you about 83. So 84 and higher, it's radioactive. It's not the only things in the world that are radioactive, but on the periodic table, if it's above that number, it is radioactive. Okay, now we know where the most active metal is, and we know why it's so reactive. It's like, whoop, give away electron, go away, go away, go away. That's what it's saying. Where's the most active non-metal? Okay, so we got some votes for this guy down here.
Wait, RN.
You think it's RN?
Yeah.
So maybe this guy?
Yeah.
Give me some more. Think. Okay, I'm going to throw some, what?
What if it's 18?
What's the most active non-metal? UUS, so we got some votes down
Yeah, I
here.
think UUS. Either UUS or 18.
I think it's 18.
Okay, so no gases are not.
All right, let me throw some things out for you. Let's start narrowing this down and see if you're right. Does anything in this last column want to react?
No.
Why not? It's a noble gas, and what do noble gases have? Full shells. So when they go out into the big wide world, they're like, leave me alone, I'm happy, I've got my full shell, so they're not reacting at all. Those guys are like, chill. Okay? Now we are down to this right here, AT and UUS. Think about what nonmetals want to do. When they go out and about on the town, they're all dressed up, right? They got their tuxedos and their ball gowns on, and they're going out and about on the town. What are they going to want to do in order to get a full valence shell? They want to gain an electron. Okay? Think about that for a second. So now we have electrons being gained. The positive nucleus, my head, if it has a positive effect, to hold on to an electron, does the electron want to be close or far away in order to gain it? Close. We want that positive to have a lot of effect on the electron shells. So if I have my head, which is my nucleus, and I want to add an electron to that shell, the positives that are here they have to go through all of these layers to have any effect out there. But if I take these off, maybe, and I'm just dealing with 2 shells, let's say, or even 1. I'll go 2. Okay? My positives have a very strong pull on this shell. You want to change your answers now? Winner, winner, chicken dinner. Strongest nonmetal, because the protons can pull through these 2 little shells and hold on or pull electrons away from somebody else. You see how these are on opposite sides of the periodic table? Okay? This fluorine is he's the bully. This guy's the bully. He's the bully of the periodic table. If you find a fluorine in a cold, dark alley, that fluorine is going to grab your electrons away from you. He is. Just the way it is. And who's going to win the fight? Fluorine. Because his nucleus is so close to that shell. If I added another one, even though I'm adding more protons, you still have to go through these 2 shells for it to influence what's happening in this 3rd shell. So fluorine is a small radius. The atom's radius is measured from the nucleus to the outside energy level. What is happening back there? You all right? It has a fairly strong nuclear charge based on a small radius. Does anybody else need water while Panak is going to fill up his water bottle? You want water? He can fill yours up.
Oh, I'm not filling my water bottle.
Come on. Give him all to Panak. He wants to go get water. You don't all need to go.
I love H2O. Here, Bernard, come here. I got you. Yo, you already have water. You don't need water. Oh, no, I do. I have to go to the south. It has to go to the south. Wait, no, I'll drink some drink.
Do you need a basket? Carry them all in?
No, I'm chilling.
Okay.
I'm not gonna drink some more.
Are you going to be strong?
I drink some more.
For 9 years.
Oh, I will be. Grab you another water bottle.
Panak, we got more. Who's going to ask to go get water next?
Should I go with
20
him?
minutes.
No.
Nobody else will ever want to fill up their water in the room.
Just don't do that thing for a while. Give him
I'm cool too.
Dude, that's crazy. That's insane.
I want to take my
That's where you there.
go.
Oh,
Take your pass. Go fill up the water. Anybody else want water?
I actually need water.
Oh, Lordy B. All right, we'll see you later. Aren't you glad you asked if you could go get water?
I am now.
He's just failing the test.
I'm basically done. All right. Any questions on the most reactive metal, the most reactive non-metal? Metallic character. We will revisit this next week when we do periodic trends. What's the most metallic character? Who has the most metal properties? Francium. Who has the most non-metallic properties?
Fluorine.
Fluorine. Good. As you go from left to right, what happens to the metallic character? It gets less. You get less metallic as you go this way. What happens to the metallic character as you go down? It increases. It's hard to see it over here because they're all metals, but if you look here, boron is a non-metal. Aluminum and gallium. Aluminum is a metal. Okay? Gallium, and they get more metallic. Actually, this one would be better. Here, take this one. Carbon is a non-metal. What's silicon? Metalloid. Germanium is a metalloid. And then we got metal. So we got carbon, non-metal, metalloid, metal. See how it becomes more as a metal as you go down?
They're metalloid, right?
What?
That's the stairs.
If they touch the stairs, let's highlight the metalloids. I think I did it already, but we'll do it one more time. Here's your staircase. Okay? Here's your metalloids. See how they're all sitting on the stairs? Okay? And then these two, germanium and antimony. Those are your metalloids.
Okay.
UUT? I don't know. What does it say down at the bottom? The systematic names and symbols for the elements of atomic numbers 113 and above will be used until the approval of the trivial names by the IUPAC. So basically what it's saying, okay, is these guys down here have not yet been named by a group of scientists called the IUPAC.
So wait, have you not found them yet?
Yeah, well, no, we have found them. They have not been named. That's not true. They have not been named in the 2011 version. As of right now, they have been named. We can look them. I don't remember. They have like weird names.
So wait, could I get named as an element?
I want
No, I want to be like, I can be named as an element. That'd be
They can, they just haven't yet. So 113 is now called nihonium with the symbol NH. Let's see if we can find nihonium. Let's see. 113, 115, 117, and 118 names are finalized by the IUPAC. Nihonium, moscovium, tennessine, and oganesson complete the 7th row of the periodic table. Does it say when this was? 2016. Your reference tables are the 2011 version. That's why there's no name on them.
Wait, what's 14 and 16?
Maybe they didn't finalize them yet. Because remember, there's a group of scientists out there, and that's their job, is to come up with the rules for the names. Should we see if 114 and whatever got named?
They're on the periodic table. It's FL and LZ.
But maybe they're not 100% approved. Let's see. 114 and 116. fluorovium, which was names for elements 114 and 116. September of 2012 they were named. So we've got fluorovium with the symbol FL and livermorium with symbol LV.
Livermorium.
I don't know. And they were named by this group. When you see this IUPAC, International Union of Physical and Applied Chemists, you're going to see it. Regents is going to throw it on there. It's just a group of people. They're going to say, what is the IUPAC name for? It's not anything you have to worry about because I'm only teaching you IUPAC names. So when we name stuff, I'm going to say, what's the name of this? And then the Regents is going to say, what's the IUPAC name for it? You just name it the way we've always learned how to name things. Wow. Speedy. All right, I'm going to stop the tape.